Alright, let's start. So today's our first lesson. As I said, we'll be covering the first two topics. Let's start by looking at the topic one, some basic concepts in geometry. Let's make sure we're talking about the same language. Okay, first, very basic fundamental concepts. Points. Since you can't move on your point in any direction, we say a point has 0 dimensions. So a point is just a dot, which is a very simple concept. In order to tell one point from another, usually we'll label them with capital letters such as point P here. And next concept is about segments, or sometimes we call them line segments. If there were a straight path from one point to another, that path would be called a line segment, or in short, just a segment. The 2 points at the end of the segment are cleverly called the endpoints of that segment. We use these endpoints to label the segment. For example, we use this notation here to denote AB is a segment from A to B. To denote the length of that segment, we just omit the bar on top of that. For example, if segment AB equals 1.5 inches, you just say AB equals 1.5 inches. Do not write the bar on top of it. All right? Okay, next. The concept of midpoint. A midpoint is a point halfway between the endpoints. Because the midpoint is the same distance from both endpoints, we say it's equidistant from the endpoints. Be clear? Okay, next concept is rays. If we start at a point, then head in one direction forever, then we form a ray. Our starting point is the vertex of the ray, and we denote the ray as this. AB. Be careful, this is a arrow on top of AB. When the first point is the vertex of the ray A. So here, the vertex is also called origin. So if you have a ray AB here, point A is also called origin. Okay, next is the concept of lines. If we continue a line segment past this endpoint forever in both directions, then we form a line. Usually we'll use this symbol to denote a line, because a line can extend indefinitely to both ends, right? So we'll use bidirectional arrow to denote AB is a line. Sometimes we can also use a lowercase letter to denote a line. For example, you could use letter K here. Okay, next concept is about collinear and concurrent lines. If 3 or more points are all on the same line, we say the points are collinear. And if 3 or more lines all pass through the same point, we say the lines are concurrent. Be careful with these two concepts here, which are illustrated in these two figures. Are you clear? Okay, so what's next? After lines, we have planes. Planes are two-dimensional objects. On a surface like this page, for example, or this screen, we might call our dimensions left, right, and up, down. If the page extended forever in every direction, we'd call it a plane. A two-dimensional or 2D object is an object that can only has 2 dimensions, such as length and width, and no thickness or height. A 3-dimensional or 3D object is an object with 3 dimensions, length, width, and height. So in our future lessons, we'll have a look at different shapes in 2D space and 3D space, respectively. Okay, are you clear with the concepts? Okay, let's do a quick exercise. The person named Alice is thinking of a line. How many points on that line does she need to show Bob, another person, in order for Bob to know exactly which line she is thinking about? So I'll give you 2 minutes to think about this question. And if you finish, please give me your answer in the chat box, okay? Okay, since you finished very quickly, let's have a look at the solution. So the answer is 2, right? Because if Alice just gives Bob 1 point, you can't tell which line Alice is thinking about because there might be infinite number of lines that pass through this point, right? Bob can't tell which one is Alice's line. However, once Alice gives Bob a second point on the line, for example, there's another point here on that line, then he knows for sure which line is hers because there's only one line through any 2 given points, the continuation of the segment that connects 2 points. Therefore, Bob needs 2 points to determine Alice's line. Okay, next let's do another exercise. M is the midpoint of segment AB. So we use this notation to denote AB is a segment. Remember that? And N is midpoint of segment BM. And if BN equals 4, then what is AB? Again, when you finish, please give me your answer in the chat box. Alright, let's have a look at the solution together. So M is the midpoint of AB. Basically, you can draw a diagram to show the situation here, right? And N is the midpoint of MBM, so N is here. Then we know Bn is 4. Therefore, if N is the midpoint, Mn is also 4, right? So MB is 8, and then M is the midpoint of AB, then we know AB should be 16, right? Okay, very good. Okay, so next concept is circles. So basically, circles is a set of all points that are the same distance from a given point. The given point is called the center of the circle, and the fixed distance is called the radius. So for example, in the diagram on the left, O is the center, OA is the radius. We often refer to a circle by its center using this symbol here. Circle O. Circle O refers to a circle that is centered at O. A line that touches a circle at a single point is called tangent to the circle, while a line that hits the circle at 2 points is a secant line. A segment connecting 2 points on the circle is called a chord. And a chord that passes through the center of the circle is called a diameter. Okay, some trivial concepts here, which you need to be clear. The portion of a circle that connects 2 points on the circle is called an arc. Well, we denote the endpoints of the arc. Mn is a shorter arc that connects M and N. So, for example, if you have a circle O, if this is M, this is N. Well, if you see a notation here, Mn, usually that denotes the shorter arc from point M to N, not the longer one. Alright? If you want to denote the longer one, usually you will use another point here. For example, let's call there's another point P. Then if you want to denote the longer arc, here you should use 3 points, M, P, N. This is a longer arc. Alright? So the set of all points that satisfy the specific conditions is called the locus. Yes, of course. Elliptic also be a locus. That is correct. A circle is also a locus, right? Because you can use an equation to denote a circle. We'll talk about the equation of circle in analytical geometry in our future lessons. All right. So here, as long as you have a basic concept of the circle, that's fine. We'll talk about circles in our future lessons. All right. So for example, here in this diagram, OA is a radius, segment MN is called a chord, line MN is called a secant line, and L, which touches the circle only at one point, is called a tangent line. MN is a shorter arc, and PNM here is the oh, sorry, there's a typo here. MN is the shorter arc, so suppose there's another point Q, then MQN is the longer arc, right? Okay, let's do an exercise here. In the figure at right, identify whether each of the following is a secant line, a chord, a radius, or a diameter, or a tangent line of circle O. Again, I'll give you 1 minute to think about this by yourself, and then we'll have a look at the solution together, okay? Okay, how about CO? The segment connects the center of the circle to a point on that circle. So it's a radius, right? The radius of that circle. So how about line EF? Well, it seems that it only touches the circle at one point, right? So it's called a tangent line of that circle. And CD, segment CD is called a chord. Segment AB, which is a chord, and pass through the center of that circle. Therefore, it's called the diameter of that circle. And also, it's a chord of that circle, right? How about line CD? Line CD touches the circle at 2 different points, so line CD is called a secant line. Any questions? Alright, good. If no questions, let's consider another question. Another quick quiz. What is the maximum number of possible points of intersection of a circle and a triangle? Well, we haven't learned the concept of triangle formally, right? But here, simply speaking, a triangle is formed by connecting 3 points with line segments. So what is maximum number of possible points of interaction of a circle and a triangle? Yes, the answer is 6, right? Line segment can intersect a circle in at most 2 points, right? So if you draw a line here, draw another line here, draw another line here. This is a this forms a triangle, right? Since the triangle consists of 3 line segments, the maximum number of intersections between a triangle and a circle is 3 by 2, which is 6, right? Okay, next, let's briefly review the concept of compass and straight edge construction. So straight edge and compass construction is the construction of lengths, angles, and other geometric figures using only an idealized ruler and a pair of compasses. The idealized ruler, known as a straight edge, is assumed to be infinite in length, have only one edge and no markings on it, so you can't measure things using a straight edge. The compass can be proved to transfer distances. When performing constructions with straight edge and a compass, you can only draw line segments and circular arcs. You cannot use a ruler to measure segments. So in geometry, the compass and straight edge construction problem, you can only the operations you can only perform are as follows. First, given a point, you can draw any line through that point. Second, given 2 points, you can draw the line that passes through them both. Third, given a point, you can draw any circle centered at that point. And next, given a point and a segment, you can draw the circle with the center at that point and with radius equal in length to that length of the segment. And last, given 2 points, you can draw the circle through one point such that the other point is the center of that circle. Are you clear? Okay, and let's see an example here. So use your compass. Do you have a compass at hand? Alright, so if you don't have a compass at hand, just use your imagination to see if you can finish this using a straight edge compass only. Use your compass to find a point y on K such that AB equals XY. You cannot simply use a ruler to measure AB. Okay, remember, when you use a straight edge, you can't use it to measure things. So how do we do this? Okay, so the solution is very simple, right? All we can do with a compass is draw circles or parts of a circle. So to find the point that is AB from X, we first open our compass to a wide of AB, right? Open your compass to the wide of AB by putting the point of the compass at A and the compass pencil at B, or vice versa. Then we can measure a circle with center X, and this opening as a radius, since this circle X has a radius equal to AB. And 2 points where it hits K are AB away from X, right? So basically this distance is AB, this distance is also AB. Therefore, we can take either one of these as our point Y. So we could say Y is here, or Y could also be here. You get it? Very basic straight edge and compass problem. Okay, let's see another one. Shown below are segments AB and MN. First question, use straight edge and compass to construct the line segment and has length AB plus MN. Also remember, you can't just measure with a ruler, okay? Second question, construct a line segment that has length AB subtracted by MN. Can you do that? Okay, let's do this together. For question A, we can start by drawing a line K first and choose a point P here, right? On line K. We find a point that is AB plus MN from point P in two steps. First, we could find a distance of AB from point P using our construction technique in the previous problem, right? We do so by opening our compass to width AB and use this radius to draw a circle centered at P. So basically, you can find another point either here or here. So we can choose this point here, right? So we take one of our points where this circle hits K to be point, let's say it's Q. Then this length is equal to the length of AB. Then we find a point that is MN from Q by opening a compass towards AB, MN, and using the radius to draw a circle centered at Q. As shown here, this circle hits K at 2 points again, R or R prime. For example, you could take R here. Then this length from Q to R equals the length of MN. Therefore, the segment from P to R gives us AB plus MN, right? And if you want to find AB minus MN, then you should find R prime here. Then this length here from P to R prime is AB minus MN. You see that? Any questions? Alright, if you don't have any questions, next let's briefly review the concepts of axioms, theorems, and conjectures. So in geometry, an axiom, or sometimes called postulate, is a statement that is taken to be true without proof, to serve as a premise or starting point for further reasoning and arguments. Whereas axioms can be combined to prove more complicated mathematical statements. We call such proven mathematical statements theorems. So basically, when you learn theorems, you have to try to prove them to be true. A mathematical statement that is not axiom but hasn't been proved false or true is called a conjecture. Are you clear? You see the difference? Axioms, theorems, conjecture. So I'll give you some examples of axioms which we don't need to prove. Okay, it's generally accepted to be true. First, any 2 points can be connected by a straight line segment. Second, Any line segment can be extended forever in both directions, forming a line. And third, given any line segment, we can draw a circle with a segment as a radius and one of the segment endpoints as center. Next, all right angles are congruent. Also, we'll talk about the concept of right angles and what we mean by congruent in our next lesson. And last, given any straight line and a point not on that line, there is exactly one straight line that passes through the point and never meets the first line. So basically, in high school geometry, this is our starting point. We need to prove any other theorems by using these basic axioms. So I'll give you some time to have a look at these basic axioms. And next, I'll give an example of theorem. Alright, have we finished? Okay, next let's have a look at an example of theorem. This is a very typical theorem in geometry, which is called Pythagorean theorem, which states that in any right triangle, the sum of the squares of the legs equals the square of the hypotenuse, which means leg square plus leg square equals hypotenuse squared. So we'll try to prove this in our future lessons. So here is just an example of theorem. You need to prove that it's true based on these axioms. Okay, last example of conjecture. For example, Arthur is making figures for an art project. He drew polygons and some of their diagonals here. From these examples, Arthur made his conjecture. If a convex polygon has n sides, then there are n minus 2 triangles formed. One diagonals are drawn from any vertex of the polygon. So at this point, we haven't proved it right or wrong. Therefore, this statement he made is called a conjecture. Are you clear? Okay, so that wraps up our first chapter or first topic. And next, let's have a look at the second topic, which is about angles. We'll be having a look at the basic concepts related to angles. Okay, first of all, let's have a look at the definition of an angle. When two rays share an origin, they form an angle. So in the diagram at left, rays OX and OY share the same origin O, right? We can refer to the angle they form as XOY, which we use this notation here to denote an angle. So this symbol here tells us we are referring to an angle. The common origin is called the vertex of that angle, and rays OX and OY are called the sides of that angle. Notice that when we write an angle as angle XOY, we put the vertex in the middle. We could also refer to the angle as angle YOX, but not as XYO. Okay, be careful with that. When it's very clear that what angle we're talking about, we can just name it with the vertex. So basically, if there's no confusion, you could just use a one letter to denote the angle. For example, in this diagram, when you refer to angle O, there's no confusion, right? But when you have another ray here, for example, another point Z, you can't use angle O here because there will introduce some confusion. When you see angle O, reader will not know whether this angle is here, here, or here, right? So of course, two intersecting lines also make angles. Lines, for example, in the diagram on the right, lines A, B, and CD at right intersect at point P. Here we can't just write angle P, since there are many different possible angles this could mean, right? Such as angle APC here, angle APD here, angle DBP here, and angle BPC here. We might even be referring to angle APP, right? Which is actually a straight angle. Now that we know what angles are, then next we need a way to measure them so we can compare one angle to another. So how do we measure or draw an angle using protractor? Usually when you have an angle here, we line one side of the angle to the baseline of your protractor, and the other arm of that angle falls within a marking here, right? Then you read that number here to measure the given angles. For example, here, this angle measures about 62 degrees, right? So do you know how to do this using a protractor? So if you already know how to do this, we'll just pass this, okay? Is that okay? Alright, so next let's do an exercise. So here's the diagram below shows 4 common angles. In each case, point O is the center of the circle. Angle AOB cuts off a quarter of a circle. Angle COD cuts off 1/3 of a circle. Angle EOF cuts off 1/12 of a circle. And angle GOH cuts off 1/8 of the circle. Can you answer each of the questions below? And when you finish, please give me an answer in chat box, okay? Do not use a protractor. Alright, if you finish, let's have a look at the solution. So we already know that a whole circle is 360 degrees, right? Therefore, for the first question, if it cuts off a quarter of a circle, then we have a quarter by 360 degrees, which gives us 90 degrees, right? The angle AOB is 90 degrees. Question B, angle COD cuts off a third of a circle, that's a third times 360 degrees, which gives us 120 degrees, right? Angle EOF cuts off a twelfth of a circle, so that's a twelfth of 360 degrees, which gives us 30 degrees. And next, angle GOH, which is 1/8 of 360, and this gives us 45 degrees, right? Okay, let's have a look at another example. Given that angle WOY equals 60 degrees and angle WOX equals 20 degrees, can you find angle XOY? Okay, WOX is here, 60 degrees, right? Oh, sorry. WOY is 60 degrees. WOX is 20 degrees. Then we know WOX plus XOY equals WOY, right? Therefore, we have angle XOY equals angle WOY subtracted by angle WOX, which gives us 60 degrees subtracted by 20 degrees, which is 40 degrees, right? Again, very straightforward question. Any questions? Okay, if you're fine, let's consider another one. Suppose instead of measuring an angle the regular way, we go the long way around, as shown in the diagram on the right. The regular angle PQR has measured 40 degrees. What is the measure of long way around the angle? So if you turn a full round, that's 360 degrees, right? So let's call this angle alpha here. So alpha just equals a full round is 360 degrees, subtracted by this angle here, which is 40 degrees, then alpha measures 320 degrees, right? Also very straightforward concept. Can you follow me? Alright, then next let's have a look at the concept of different types of angles. Angles can be classified by their measures. A 90-degree angle is called a right angle. Lines, segments, or rays that form a right angle are said to be perpendicular. An angle smaller than 90 degrees is called an acute angle. An angle is between 90 and 180 degrees is called obtuse angle. The angle that measures 180 degrees is called a straight angle. An angle of more than 180 degrees is called a reflex angle. So again, these are some trivial concepts you need to be careful with, okay? Are you clear? Alright, then let's do a quick quiz. Can you categorize each of the following angles? First angle, alpha equals 15 degrees. So according to the definition, it's a acute angle, right? So we connect it here. Second angle, beta equals 90 degrees. Any angle that measures 90 degrees is called a right angle. Next one, theta equals 120 degrees. It's larger than 90, less than 180. So it's called obtuse angle here. Next one, gamma equals 300 degrees, which is more than 180 degrees, right? So it's called a reflex angle. And last one, phi equals 180 degrees. So it's a straight angle exactly, right? Okay, so have a look at the concept here again. Make sure you don't confuse them, okay? Alright, so we have talked about different types of angles, and next let's have a look at different relationships of angles. Okay, first of all, we call angles that share a side adjacent angles. For example, if you have a diagram here, we have three angles here, right? Angle WOX, XOY, and WOY. So here, WOX and XOY are adjacent angles because they share the same side OX. Are you clear? Okay, secondly, supplementary angles. We call two angles that add up to 180 degrees supplementary angles. For example, if you have two lines intersecting at a point X here, then we know that angle WXY plus angle YXZ equals 180 degrees, right? Then we call angle WXY and angle YXZ are supplementary angles. Are you clear? And similarly, we have a concept of complementary angles. We call angles that add up to 90 degrees complementary angles. For example, in the diagram here, we know angle AOC plus angle BOC equals 90 degrees. Then angle AOC and angle BOC are called complementary angles. Okay, so be careful with the concept of supplementary angles and complementary angles, okay? Do not confuse them. And next we have a concept of vertical angles. The pairs of angles such as MPN here and LPO in the diagram below are called vertical angles. LPO and MPN are vertical angles, And similarly, angle MPL, which is angle here, and angle NPO, which is angle here, are also vertical angles. Okay, clear? Okay, if you don't have any questions, let's do a quick exercise. If lines LN and MO intersect at point P, can you prove that angle MPN equals angle LPO? Well, it seems obvious, but remember, we need to prove that, right? So I'll give you 2 minutes to think about that, and after that, we'll have a look at the solution together, all right? Okay, have you finished? So how do you write the proof using mathematical language? So we could write it like this, right? First of all, we know angle LPM plus angle MPN equals 180 degrees because it forms a straight angle there, right? And secondly, we also know angle LPM plus angle LPO is also 180 degrees because it also forms a straight angle, right? Let's call this equation number 1 and this is equation number 2. We could use equation number 1 subtracted by equation number 2. This gives us the left side becomes angle MPN minus angle LPO, right? The right side equals 0. Therefore, we have angle MPN equals angle LPO, right? Can you follow me? And this gives us a very important conclusion, which means vertical angles are equal. So you could consider this as a theorem, right? Because we have just proved this. Any questions? All right, if you don't have any questions, let's take a 10 minutes break, and after that, we'll have a look at the second half of today's lesson. Is that okay? 10 minutes break. Alright, next let's talk about the concept of parallel lines. So in geometry, if two lines are coplanar means it must be on the same plane. If two lines are coplanar and do not intersect at any point, we say that they are parallel. If lines A, B, and C are parallel, we write it like this. Line AB is parallel with line CD. We use this notation here. Also, if you want to label two parallel lines, you can use arrows. Or if you want to label a set of parallel lines, just use the same arrow to denote, for example, K, J, and L are parallel. And another pair of parallel lines here, M and N, then you could use double arrow here to denote M and N are also parallel. So here this diagram shows two sets of parallel lines. Be clear? Okay, next, the concept of angles between a transversal and two parallel lines. So the setup is, if you have a pair of parallel lines M and N, M is parallel to N, and another line L cuts across parallel lines M and N, then line L is called a transversal. Then it forms a series of angles here. And these sets of angles have their names. Angle A and E are called corresponding angles. D and F here, D and F are called alternate interior angles. A and G are called alternate exterior angles. C and F are called same side interior angles. And B and G are called same side exterior angles. Are you clear with the names? Any questions? Okay, let's do a quick quiz. So here we have a transversal line which cross with line M and N. M is parallel to N. So can you connect each pair of angles to its correct name? A and E are called, so according to the definition previously, A and E are called corresponding angles, right? How about D and H? D and H are also corresponding angles, right? You see that? Angle B and F, again, they are also corresponding angles. C and G are also corresponding angles. How about D and F? D is here, F is here. They are called alternate interior angles, right? And C and E, C is here, E is here, are also alternate interior angles. D and E are called same side interior angles, right? And C and F are also called same side interior angles. Are you clear? Okay, so next let's have a look at properties of parallel lines. So if you have a series of parallel lines, they have some properties. So let's have a look at property statement 1. If two parallel lines are cut by a transversal, then corresponding angles are congruent. Congruent basically means equal. So let's have a look at the example here. So if you have M is parallel to N here, cuts off by a third line L, then we have the following relationship. The corresponding angles are congruent, such as A equals B, C equals D, E equals F, and G equals H. Okay, so this is a property theorem 1. So let's go over all the theorem first. Then remember, for each of the theorems, we need to prove them. Alright? Okay, property theorem 2 states that if two parallel lines are cut by a transversal, then alternate interior angles are congruent. For example, if in this diagram M is parallel to N, L is a transversal, then we have the following relationship. A equals B and C equals D. In alternate interior angles are congruent. This is a second property of parallel lines. Are you clear? Okay, third property states that if two parallel lines are cut by transversal, then same side interior angles are supplementary. For example, in this diagram here, M is parallel to N, L is transversal, then we have the following relationship. A plus D equals 180 degrees, C plus D also equals 180 degrees. Same side interior angles are supplementary. Are you clear? Okay, next, property 4 states that if two lines M and N are parallel, then every point on line M is located at exactly the same distance from line N. For example, if M is parallel to N here, A is arbitrary point on line M, and segment AB is perpendicular to N, then we have, if M is parallel to N, then AB must be a constant. Okay, so we have learned 4 of the properties of parallel lines, right? The problem is, can you prove each of them? Well, actually, the first one is the hardest one because we haven't learned any other theorems yet, right? So let's try to prove the first one. If the first one is proved, all the other theorems can be easily proved. But to prove the first one, all you can use is just the Euclid's 5 axioms, because we haven't learned any other theorems yet, right? So first of all, let's recall Euclid's 5 axioms or postulates, which states that first, a straight line segment can be drawn joining 2 points. Then any straight line segment can be extended indefinitely in a straight line. Third, given any straight line segment, a circle can be drawn having the segment at the radius and one endpoint at the center. Next, all right angles are congruent. Last, if two lines are drawn which intersect a third in such a way that the sum of the inner angles on one side is less than the two right angles, then the two lines inevitably must intersect each other on that side if extended far enough. This postulate is equivalent to what is known as parallel postulate, which is equivalent to say, given any straight line and a point not on it, there exists one straight line which passes through that point and never intersects the first line, no matter how far they are extended. So these are the only axioms you can use to prove the property theorem 1. So I'll give you 2 minutes to think about this property to see if you can prove this by yourself, okay? So the problem is here. Given that M is parallel to N, L is a transversal, can you prove angle A equals angle B in this diagram? All right, let's have a look at the solution together. So if you go back to the Euclid's 5 axiom, it's probably useful for the fifth one. We can use the fifth one to prove this property is true, right? So first of all, we could assume A does not equal B. If you assume A does not equal B, that means A is either greater than B or A is less than B, right? So without loss of generosity, this WLOGB means without loss of generosity, we could assume A is greater than B, right? So what will happen if A is greater than B? Then we will have because of A plus C equals, well, let's call this angle here is C. Because we have A plus C equals 180 degrees, right? Then we know B plus C must be less than 180 degrees. Can you see that? If you substitute A using B, then B plus C must be less than 180 degrees, right? And according to the Euclid's fifth postulates, if two lines are drawn which intersect as third in such a way that sum of the inner angles on one side is less than two right angles. So here we have sum of the two angles which is less than two right angles, right? Then the two lines inevitably must intersect each other on that side if extended far enough. So this tells us that according to Euclid's fifth axiom or postulate, M and N must intersect on the left side, right? Also note that if we assume A is less than B using the same method, we could have M and N must intersect on the right side. And obviously this contradicts with the fact that M is parallel to N, right? They could not intersect at any point. Therefore, our assumption is not correct. If your assumption is not correct, that means A does not equal B. This is not correct. Therefore, we have A must equal B, right? Did you get it? So this is how we can prove the first property. And then based on the first property, the following properties are very easy to prove, right? So can you prove the second one, the second property, using what we have learned so far? Well, of course, you can use Euclid's fifth axiom or any theorem that has been proved as a base, right? Okay, let me show you the result. Let me show you the question here. The question is, can you prove the second theorem of parallel lines? The question is, given a diagram like this, M is parallel to N, L is transversal, can you prove A equals B? So because we have already proved the first one, you could use the first theorem to help you prove the second theorem, right? So let's have a look at the proof here. Again, we introduce another angle C here. So because we have M is parallel to N, right? Then we have C equals B. Because they are corresponding angles, we have proved that if you have a pair of parallel lines, then corresponding angles must equal, right? So then we could directly use that theorem. If M is parallel to N, then C equals B, right? And because we also have C equals A, we have already proved that vertical angles are equal, right? Therefore, we have A equals B. You see that? The second one is very easy to prove. And property 3 is similar, which is very easy to prove. Because we have M is parallel to N, we have B equals C, because corresponding angles are equal. So C is here, right? And because we have A plus C equals 180 degrees, therefore we have A plus B equals 180 degrees. Therefore, we have proved that given M is parallel to N, L is transversal, we have A plus B equals 180 degrees, right? Okay, I'll leave the fourth one for you at home to prove, okay? Try it by yourself to see if you can prove the fourth property of parallel lines. Okay, so if you don't have any questions, let's consider a quick quiz here. Line M and N are parallel, and we have given the measure of one angle in the diagram as shown. Can you find the values of the remaining angles A, B, C, W, X, Y, and Z? And if you finish, please give me your answer in the chat box in the following order: A, B, C, W, X, Y, and Z. All right. Okay, let's have a look at the solution together. So here A equals 180 degrees minus 113 degrees, which gives us 67 degrees, right? And then B equals A, which gives us 67 degrees. And C equals 113 degrees as well. And W equals 113 degrees. X equals B, which is 67 degrees. Y equals C, which is 113 degrees, and Z equals A, which is 67 degrees, right? Any questions? Okay, if not, let's consider another one. In the figure below, we have line AB is parallel to line CD and AD is parallel to line BC. We are also given the measures of four angles as shown in the terms of X and Y. Can you find the values of X and Y respectively? Alright, let's have a look at the solution together. So here, if you have this angle equals 3y plus 15 degrees, then because AB is parallel to BC, we have this angle here is also 3y plus 15 degrees, right? And then this angle here is also 3y plus 15 degrees. So we have first 3y plus 15, then plus x plus y equals 180 degrees, right? Because in triangle BCD, we have sum of the three internal angles are 180 degrees. It's very easy to prove, right? And secondly, we have 3y plus 15 plus 3x minus 15 equals 180 degrees. So basically, we have two unknown variables and two equations. This gives us, well, first of all, 4y plus x equals 165, and x plus y equals 60. And then we can solve 3y equals 105, right? Which gives us y equals 35 and x equals 25. Did you get it? Of course, here is x, this angle is x, and this angle is y. So, well, because we haven't learned the sum of the three internal angles is 180, so you could also use this straight angle here, right? So if you can, because this angle is the vertical angle of this angle, and this angle equals that angle here. So let's use this straight angle here instead of using the sum of the three internal angles, because we haven't learned that yet, right? Okay, we'll talk about triangles in our next lesson. So this gives us first equation. And here, 3y plus 15 plus 3x minus 15 gives us the second equation here, right? So basically, when you have two unknown variables and two equations, you should be able to solve these two unknown variables, right? Okay, so if you don't have any questions, now the question is, how do we test if two lines are parallel? And there are actually a number of testing theorems. Again, first let's have a look at these testing theorems. Then consider how do we prove them. There are four testing theorems. Testing theorem 1 states that if two lines are cut by a transversal, if corresponding angles are congruent, then the two lines are parallel. For example, in this diagram shown here, if you have angle A equals angle B, then we can conclude M is parallel to N. This is called testing theorem 1. Are you clear? Okay, and after that we have the second testing theorem, which states that if two lines are cut by a transversal, if alternate interior angles are congruent, then the two lines are parallel. For example, in this diagram, if you have angle A equals angle B, then you can conclude line M is parallel to line N. Are you clear? And testing theorem 3 states that if two lines are cut by transversal, if same side interior angles are supplementary, then the two lines are parallel. For example, in this setup here, if you can prove A plus B equals 180 degrees, then you can conclude M is parallel to N. Are you clear? The last testing theorem states that if every point on line M is located at exactly the same distance from line N, then M is parallel to line N. For example, if you have a diagram like this, A is an arbitrary point on line M, and AB is parallel to N. If AB is a constant, then you can conclude M is parallel to N. So basically, each of the testing theorems is a reverse statement of the property theorems we have already talked about, right? So the question is, how do we prove each of the testing theorems here? Again, you could use what we have learned so far, or the Euclid's 5 axioms. So the very basic theorem, testing theorem, is the first one. If you can prove the first one is true, then the rest of the testing theorem is very easy to prove, right? So now let's consider the first theorem here. The question is, given A equals B here, can you prove line M is parallel to line N? So I'll give you 3 minutes to consider this question here, and we'll have a look at the solution together after that. All right? Okay, have you finished? Let's have a look at the solution. So, well, we could assume the opposite. For example, we could assume m is not parallel to n, then see what will happen. If we assume m is not parallel to n, then m and n must intersect, right? We assume m and n intersect at some point O. So in that case, we have m is here, n is here. They intersect at point O. So let's choose any arbitrary point on line M. From point A, we could make another line FC. Let's call it FC. So from point A on M, we could make another line FC, which is parallel to the other line N, right? Then we know that FC must be different with line M, right? Then we have FC and at line M must be different lines. And because we have FC is parallel to line N, and then we have angle DAF. Well, let's call point, let's draw another line here, okay? Let's call it point D here, and this point is B. Then we have angle DAF equals angle B here. And because if you consider another angle here, because A equals B, this is a given information, right? We have angle GAF. So this point here is G. GAF, which is the angle here, must equal 0 degrees, right? And this fact contradicts with the fact here, with the conclusion here, with statement 1. Therefore, your assumption here is not correct. Then we have proved M is actually parallel to N, right? So this is a whole logic you can use to prove if given A equals B, then M must be parallel to N, right? Did you get it? And based on the first testing theorem, we can actually easily prove the second, third, and fourth ones are also correct. So for example, if we are given this question here, given A equals B, can you prove M is parallel to N? Now this becomes very easy, right? Because we have A equals B, well, let's introduce another angle here, C. And C equals A, because they are vertical angles, right? Then we have B equals C. And B and C are actually called corresponding angles. We have already proved that if corresponding angles are equal, then the two lines are parallel. So you can make the conclusion M is parallel to N, right? Again, similarly, I'll leave testing theorems 3 and 4 for you to prove at home, alright? And now we can make a summary here. So we have learned 4 property theorems and 4 testing theorems. Actually, each property theorem is reversible. If we reverse the property theorems, that becomes a testing theorem. So we can combine the property theorems and testing theorem together, which means, first of all, two lines are parallel if and only if corresponding angles are congruent. Second, two lines are parallel if and only if alternate interior angles are congruent. So both directions are true. Third, two lines are parallel if and only if same-side interior angles are supplementary. And last, two lines are parallel if and only if point line distance is constant everywhere. So this symbol simply means if and only if, or equivalent, which means the statement on the left side of this symbol is equivalent to the statement on the right side of this symbol, which is abbreviated as IFF. IFF means if and only if. Did you get it? Do you have any questions? Okay, if not, next let's talk about the angles in a triangle. So when we connect 3 points with line segments, we can form a triangle, right? Concept is very straightforward. The points are called vertices of that triangle, and the segments are called the sides of that triangle. The angles inside the triangle formed by the sides are called interior angles of a triangle. When we refer to the angles of a triangle, we mean the interior angles. Be clear? Okay, another concept. When we extend a side past a vertex of a triangle, such as shown in this diagram, we form an exterior angle, which is the angle here. This angle here is called exterior angle of that triangle, such as angle XZP shown here. We call angle X and angle Y the remote interior angles of exterior angle XZP. Okay, clear? Okay, and next let's have a look at some important properties of the interior angles of a triangle. The first theorem states that the sum of the angles in a triangle is always 180 degrees. For example, if you have a triangle ABC, angle A plus angle B plus angle C always equals 180 degrees. The problem is, how can we prove this? Can you prove this by yourself? Which means, consider this question here to see if you can solve this. Prove that the sum of the measures of the angles in the triangle is always 180 degrees. For example, given a triangle here, ABC below, can you prove that angle A plus angle B plus angle C is 180 degrees? Okay, I'll give you 2 minutes to think about by yourself. Let me know if you finished, okay? So actually we can prove it like this. We could draw a line K through a point, one of its vertices. For example, we could draw a line K passing through A, such that K is parallel to segment BC, right? Then we introduced two angles here, alpha and beta. And therefore we know alpha equals angle B, right? Because they are alternate interior angles. And then we have beta equals angle C. Again, they are alternate interior angles. Remember, we are using what we have learned so far to prove a new theorem, right? And because we know alpha plus angle BAC plus angle beta equals 180 degrees because they form a straight angle, then we know angle B plus angle BAC plus angle C is 180 degrees. Therefore, we have proved the sum of the interior angles of a triangle is always 180 degrees, right? So basically, we are making use of what we have learned so far, specifically the property of parallel lines, to prove this new statement. Then, like what you said here, if you want to prove the sum of the quadrilateral is 360, you can divide this into two triangles, right? You have 180 here, 180 here, then the sum of the interior angles of a quadrilateral is 360. Did you get it? Again, we'll be learning about the concept of quadrilateral in our later chapters. Okay, the second theorem of a triangle states that any exterior angle of a triangle is equal to the sum of its remote interior angles. For example, in this setup here, angle XZP equals angle X plus angle Y. Again, can you prove this is actually true? Well, if we have already proved the first property, then the second one is very easy, right? For example, let's call this angle here alpha. Well, first of all, we know that sum of the three interior angles of a triangle x plus y plus alpha is 180 degrees, right? And also we have alpha plus angle XZP is 180 degrees because they form a straight angle, right? So again, we could use equation number 1 subtracted by equation number 2. This gives us angle x plus angle y minus angle XZP is 0, right? Therefore, we know angle XZP equals angle x plus angle y, right? Any questions? Okay, so if no questions, let's consider some other exercises. First one angle in a triangle is twice another angle, and the third angle is 54 degrees. What is the measure of the smallest angle in that triangle? And again, when you finish, please give me an answer in the chat box, okay? Okay, since you finished very quickly, let's have a look at the solution together. So basically, it's more like an algebra question, right? So suppose one of the angles is x, then the other angle is 2x, right? Then we know the other angle here is 54. Then we have x plus 2x plus 54 degrees equals 180 degrees, right? Then we have 3x equals 126 degrees, and then x equals 42 degrees. And the other angle, the third angle, 2x, is then 84 degrees. If you compare these three angles, then we know the smallest is 42 degrees, right? Very good. Then let's consider another one. So in this diagram here, M is parallel to N. AB is perpendicular to M. Angle ADC equals angle BCE equals 3x. Angle CEB equals 50. And angle BCD equals x. Can you find the value of x? Right, let's have a look at the solution together. So basically, when you consider triangle BEC, this angle can be expressed using x, right? Which is 180 degrees minus 3x plus 50 degrees, which is 130 degrees minus 3x, right? Then we know this angle here is 90 degrees because AB is perpendicular to BE. So that's 90 degrees minus 130 degrees minus 3x here, right? And this gives us 3x minus 40 degrees. Then we know this angle can also be expressed using x, which is 180 degrees minus 3x, right? And then if you consider triangle BCE, we have x plus 3x minus 40 degrees plus 180 degrees minus 3x. This will give us 180 degrees, right? So we have x plus 3x minus 40 plus 40 degrees plus 180 degrees minus 3x equals 180 degrees. So we cancel 180 here, cancel 3x here. Basically, we have x equals 40 degrees, right? Okay, very good. If you don't have any questions, let's consider the next one. Again, another angle chasing problem. In the diagram below, AB is parallel to DE, BAC is 2x minus 20, ACB equals 30, and DEF equals x plus 55. Can you find angle CED, which is this angle here? Have you finished, Daniel? Yes, of course. Help us out. Yes, AD is correct. Okay, I'll give you the solution here. So first of all, we could express this angle here using x, right? So that gives us 180 degrees minus x plus 55 degrees, which gives us 125 degrees minus x. Then this angle equals this angle here because they are alternate interior angles for parallel line AB and ED, right? So this angle here is 125 degrees minus x. So if you consider triangle ABC, we have the sum of three internal angles plus 30 degrees plus 125 degrees minus x gives us 180 degrees, right? Simplify this will give us 2x minus 20 degrees plus 30 degrees plus 125 degrees minus x equals 180 degrees. And this gives us x equals 180 degrees minus 125 minus 10 degrees, which is 45 degrees, right? Therefore, angle CED is 125 degrees minus x, which is 45 degrees, and this gives us 80 degrees, right? Any questions? Okay, so let's consider one last question to end today's class. So given the diagram below, can you find the sum of x plus y plus z? X, y, and z are external angles of a triangle ABC, right? Alright, very good. So we can actually prove the sum of x plus y plus z is actually 360, right? Because, well, let's call these three internal angles, alpha, beta, and gamma. So first of all, we know x equals beta plus gamma, y equals alpha plus gamma, and z equals alpha plus beta, right? And therefore x plus y plus z equals twice of x alpha plus beta plus gamma, which is 2 times 180 degrees, and this gives us 360 degrees, right? Therefore, you can treat this as another theorem regarding a triangle. Sum of the three exterior angles equals 360 degrees. Alright? Alright, so today we have go over the first two topics, which are very fundamental and basic concepts. And as we proceed, we'll talk about more complex concept. Alright? So see you next time, and I'll give you the homework and lecture slides together with the lecture video to our WeChat group. Okay? If you need that, you can check that from there. Okay, bye.